welded joints integrity of the thick plate steel bridges beams. The presentation is done by Dorin Radu, Faculty of Civil Engineering, Transylvania University of Brașov. The presentation is divided in 5 parts. In the first part, the introduction, the importance of the problem, fatigue analysis methods, assessment of the defects, taking into account the welded quality levels, thickness effect, thickness correction factor, and the case study of fracture assessment and the conclusion in the. If in the mechanical engineering application, the fracture mechanic approach, we do have the stress and the defect, then the design, manufacture, and in the end the service lifetime estimation and inspection intervals. In the civil engineering structure subjected to low and or high cycle fatigue, we do have the stress, then the design, take into account the service lifetime requirements, also the Eurocode provisions, Eurocode 3 Part 9, design of the steel structures fatigue loading, and Part 10, design of the steel structure, the material toughness. We, in the end, we do have the manufacturing direction of the structure, taking into account the execution quality controls, and together with the inspection intervals, we will have the defect in the end. These schemes present an importance because the existence flaws in the critical parts of a structural elements may lead to failure of sub-assemblies, and in the case of lack of redundancy, even to a collapse of the entire structure. Some problems from the investigation on site, we can see the different problems of welding joints. Also some surface notch type and surface type defects that are affecting an existing structure. This is a bridge done in Timișoara. Also, these two pictures are taken also in the manufacturing workshop. Of course, we do have details that are fatigue resistant, and we can use them. This is the case for solution presented by Professor Petzek from Political University of Timișoara. In the next slides, I would like to present the case of Rhine Bridge Leverkusen, a bridge, a steel bridge beams, with steel beams bridge, and this bridge has a problem with the increased traffic and the increased fatigue loading. In the end, in the inspection, several flaws were discovered. As we can see, mainly crack-induced flaws that are propagated in the area of the stiffeners from the main. Also some big problems in the welding and not in the area of the welding, also induced by fatigue loading, joints between main and secondary beam. More close picture of the problem. Some elements regarding the fatigue analysis procedures, more or less approaches. We do have a nominal stress approach, hotspot stress approach, effective notch stress approach, and in the end fracture mechanics approach. Regarding the nominal stress approaches, most design guidance documents related to fatigue, such as Eurocode 3 for example, are based on the nominal stress method. This is widely used approach, and the requirements are very important to have a detail free from significant imperfections. Hotspot stress approach is also included in the European standards and in the latest International Institute of Welding provisions. Important thing here is that in contrast with the nominal stress method, where stresses are computed using simple strength of material equations, The hotspot stress method requires a more complete understanding of stress components. At a welded joint, the stress through the wall of a plate is non-linear, for example, and the stress components can be separate. The effective notch stress strain approach is divided in a linear elastic and elastic plastic notch stress, respectively, strain approach. In this respect, the effective notch stress approach has an advantage over the other methods in that the stress value used in the analysis is unambiguous, since it is the maximum computed stress at a well-defined location in the finite element. Fracture mechanics method is useful for the assessment of cracks or crack-like imperfection. It requires the knowledge of the notch stress distribution in the vicinity of the crack, and also a formula for determination of the stress intensity factor. Of course, the fatigue life can be determined by using the Paris-Erdogan power law. When welded components behave like severely notched or corroded ones with a short period of crack initiation, it is reasonable to consider the crack propagation as a governing process and to use this method. Some comparisons between these four methods. We can see that the thickness effect is included only in the effective notch stress approach and the fracture mechanics approach. This is very important for the next presentation to be taken care of. The Institute of International Welding is presenting also some provisions regarding the fatigue assessment methods, taking into account the imperfections and the misalignment to consider, and also the joint classification that is determined based on the joint loading function. For example, the loading shear loaded fillet weld, or the longitudinal shear loaded longitudinal fillet weld, or longitudinal normal loaded fillet weld in the B version. The red lines indicates the fatigue critical. The imperfection and their classification is taken care by a different standard. One of these standards is ISO 5817, but it has some limits in direct application to fatigue problems due to because of it is inconsistent with respect to fatigue properties and the needs application guidance. After inspection and detection of a weld imperfection, the first step is of the assessment procedure is to determine the type and the effect of the imperfection by characterization of the type of the imperfection, following the assessment effect of imperfection. Thus, using, for example, the effective notch method, many above listed effects can be modeled as one way to show the impact on fatigue into the design of experiments. In such approach, design of experiments, the weld quality levels for fatigue loaded structure is very important. Here you can see the effect on principal stress in the weld toe for one-sided or two-sided butt joints with a nominal stress of 100 megapascal. We can see the influence of thickness in both types of joint in a positive way. Same for the fillet welds, non-loaded and non-loaded fillet welds. We can see also the influence of the thickness that is much higher for the loaded fillet. Some consideration regarding the roof side requirements. Joints with weld root as weakened point. Following the design of for-purpose principle, the analysis should focus on the identification of weakened points of toe or root when loading is applied to the component. In case of fillet walls will decrease when the thickness is increased. Very important, presented also. The thickness effect is a phenomenon that the fatigue strength of a welding connection decreases when the thickness of load carrying plate increases. It was the preoccupation of Kearney in 1981, which proposed an empirical thickness correction for fatigue strength, which is taking into account fatigue strength and fatigue life for a reference plate of thickness TB. Also in 1984, thickness correction factor for fatigue strength has been implemented for offshore design codes. Later, due to researching works of some Norwegian researchers, this factor was also included in the Norwegian standard steel design codes and many other codes. From 2008 and then in 2016, with a revised version of International Institute of Welding provisions, we do have the thickness of the plates, influence of the fatigue strength taken into account, with the respect of the fatigue class detail. So it's computed a thickness reduction factor, nominated as FT, applied to both nominal stress approach and hotspot stress approach in Eurocode 3. It is recommended to use in Eurocode 3 0.2 for some specific details for nominal stress approach. These are provisions from IIW. Causes of the thickness effect. Causes of the thickness effect are statistical production related or geometric factors. This is very important to be understood, and the geometric factors are playing an important role. From the literature, this thickness effect is taken into, as I said, in Hobacker and Eurocode 3, a different type of formulas, but the principle is the same. Some details from the literature that are presenting the influence and the result of the N factor. Some things about a case study, the fracture assessment, determining the safety of the in-service steel structure based on the fracture mechanic principles. Using an engineer critical assessment methodology, we have two phases. The first phase is to determine the acceptability of the detected cracks, and the second, the fatigue assessment of the elements containing cracks based on the loading. The needed assessment data are the stress ranges, the limit of crack growth, fatigue crack growth law, 1 or 2 slope, and types of and dimension. As the calculation of the structural element service lifetime is needed to have a load recording spectrum for a given time, the distribution of the loads, which can be rearranged using the probability density functions or variable distribution, and having the possibility to assess the flaws. Some consideration regarding the cruciform welded joints, because these type of joints were assessed through thickness flow and weld toe load carrying attachment. We can see here the computing of the flow height critic and flow critic length. And using the failure assessment diagrams, we can compute also the critical fatigue assessment of different flow cases. We can compute also the most critical depth of a flow. Some conclusions of the research deals with the effect of thickness of the elements of the welded steel plates. Basic structural integrity tools such as failure assessment diagrams can be used efficiently to determine the in-service safety of the steel structures, and it is underlying the Petzek design welding details and the influence of the crack type flaws in the overload behavior of the welded thick plate steel elements, as the future preoccupation is to detail more the welding. Thank you for your attention.